Okay. Well, again, thank you for that. Was really fabulous. And so just a reminder, here are the sections about what you do about nitrogen when it's out of the gate, so to speak. Charlie gave us a great explanation of what's happening with regards to bioextraction, and Mike Doall some more information on that. I'm actually currently pinch hitting for, or standing in for Nils Gobler. Nils Gobler is heading research at the Center on Permeable Reactive Barriers. That's going to come into place momentarily. But Nils is currently not with us. He's in the mud flats in the North Sea. He'll be with us shortly, returning, but I'm giving this presentation in his stead. And so, an incredible partner in all this work is Cornell Cooperative Extension. We have Ron Paulson here from Cornell, out in the audience, and we have Molly Graff from Cornell Cooperative Extension on our panel as well. Molly also is very proud to have be a graduate of the center. She'll be partaking in part of our panel questions. But as I was describing before, once that nitrogen is in the groundwater, there's a problem. It's been there for decades, and we know it's been rising. We've heard about that. And eventually, it's going to make its way into surface waters. We haven't treated it for decades. We're going to start now, but we need other solutions. We heard what bioextraction can do. We're going to hear more about that. But even if we stop discharging all nitrogen today, if we had this national septic system that took out all nitrogen, 100% denitrification, which isn't realistic, you'd still be dealing with that legacy nitrogen for decades. So we need a solution that's going to address that. And so what I'm going to talk about now is the work that the center's doing on permeable reactive barriers. This is part of the solution to this. And you can see via this image, the whole idea is to create a barrier that literally goes into the groundwater. It's going to intercept that groundwater as it's traveling through the aquifer. And by having material in there that's permeable, it actually brings groundwater from below it, up from the sides, into where that barrier is. So not only are you treating the groundwater where you put the actual barrier, but you're pulling in groundwater from the side. And there's been research that's been done on this, both globally, but also here at the center. You can see Molly's publication from 2020, showing that this is an effective approach for removing nitrogen from groundwater via the process of denitrification. There's some great benefits of doing this. Specifically, we've seen that as soon as you install one of these things, they start working right away. And as I mentioned before, the shoreline is a great place for putting these things in. Not only are you sucking the water in from the sides because it's more permeable, but just via the way groundwater flows, it turns out coastal water, salt water start intruding on groundwater at the shoreline. And so what you get just naturally, therefore, is the upflow of groundwater towards the surfaces. So it's a great opportunity for installing these sorts of systems. And in addition, as you'll hear a little bit in the future, there's also other opportunities that go right at that shoreline interface. Specifically, as you probably know, here on Long Island, if you go to the coastal zones, you'll see that many of our shorelines have bulkheads in them. And while bulkheads in some cases are an environmental problem, they're also an opportunity for the installation of permeable reactive barriers. These bulkheads need to be replaced all the time. And every time you do that, there's a big expense in installing a new bulkhead. As it turns out, you could probably put a PRB in the process for very little additional cost. So here at the center, we're specifically focused on coming up with recommendations on how to place PRBs optimally to ensure performance, minimize cost, and also minimize some unintended consequences. So we're addressing questions like, where would you put a PRB and what would make it most effective? How would you design it? We actually are working presently on 3 or 4 different types of designs that range from, well, I'll talk about them momentarily, and also we're thinking about the cost. And so with regard to designs, we are working on things that are trench-based systems, funnel and gate systems, something called a carbon array, I'll talk about momentarily, and even injection wells. And we're doing research on all those things, specifically trying to understand what would be the best place to put those things, what's the right material to put in, and also what might be happening with regards to other potentially unintended consequences I'll talk about momentarily. And so we're doing that in a multi-phase approach. So we're doing laboratory experiments that actually have turned out to be incredibly informative for actually ecosystem and in-ground implementation. We're putting systems in collaboration with Cornell and monitoring those. And actually, we're using all of this data together to create models that then allow us to better predict how these things may function in the future. So we've been doing a lot of work on this over the last 6 years or so. I could go on, but I'm just going to what Bill's put together really just highlights some things we've been doing recently. So you can see there, Jian, one of Niels' graduate students, next to a series of columns. You can see those columns there. As you can see, several, about 4 feet high or so. Those columns are filled with wood chips from pre-existing PRBs. But different from using different types of wood. So this is partly getting at the question, does the type of wood you use matter when it comes to a PRB? In addition, they've also been exploring how different flow rates of groundwater might affect the functioning of this PRB. So, in some cases, groundwater flows very slow, in other places it may be very quickly. And as it turns out, those are important considerations with regards to how you want these systems put together. And then also we're looking at things like temperature and then monitoring both for their nitrogen removal, but also other things like you see GHG, that's greenhouse gas formation. And I'm going to get more into that. But obviously, we don't want to be in a situation where we're solving one problem and creating another. And that's something that really no one had really thought about, but Niels had thought about coming into all this. That is to say, what's the possibility that if you overtreat, you may be forming greenhouse gases? I'll talk about momentarily, and also talk about oxygen. Of course, all the removal of nitrogen has to happen in an anoxic condition, right? In order to have denitrification. So you need to be monitoring the levels of oxygen as you go along as well. So here's one of the first data sets. You can see the different colored bars here. On the y-axis is the actual nitrogen that's getting through each of these columns, and each column operating like a PRB. You can see the colorized bars are the different types of wood chips. And you can see the different types actually do matter. And then the different clusters of bars are different flow rates of groundwater. And that also matters. Right? The faster the groundwater is flowing, the less you're actually going to remove. So just to highlight a few things, firstly, here's our pine wood chips actually not being a great performer and actually not doing as well as other wood chips. If we up the flow rate, well, some of the other wood chips start doing poorly also, but oak ends up being the best performer. And even at higher flow rates, we're getting full nitrogen removal. Now, Niels is a very innovative scientist. And one of the things that he's done a lot of incredible work with, along with other scientists at the Center of Clean Water Technology, are using things such as planar optoid imaging. And so what you see, the very first picture there are the actual wood chip columns. But then what you see next to them, the two black images with the colorized images, are those same columns. But now they've been outfitted with a planar electrode that actually detects the level of oxygen. He actually makes movies of these, which I'm not going to play today, but the movies are incredible because you can see literally over time, as flow rate changes, how the oxygen levels change. So if you look at the first set of colorized images, that's at a flow rate of about 1.9 feet per day of groundwater. And what you see is, and the flow is going from the bottom to the top, right? So you see some color at the bottom, but by the time you get to the top, you see very little for most of those different types of columns. But when we up the flow rate, and that's the far panel on the right, to a higher flow rate, but these are realistic, these are flow rates we see for groundwater coastal zones. What you start to see is that there are differences, and in fact, what he shows here is that the pine is actually letting, because of that high flow rate, letting more water through, and there's oxygen going all the way to the end. And that actually explains the result. You can't have denitrification in the presence of oxygen. So that's one of the drivers here. Another thing that Niels wanted to look at is specifically the formation of methane. For those of you who are not aware, of course, CO2 is driving our global climate change problem, but methane is a far more potent greenhouse gas. And so Niels is concerned with regards to the production of methane coming out of these columns. And so as it turns out, these PRBs are actually a fine balance between these two compounds. So if you look at these two graphs are in parallel, and so these bars go with these here and so on and so forth. But essentially what this shows you is that even though the pine was letting through nitrate, it was forming no greenhouse gases. What happens is if you get rid of all the nitrate, well, the microbes are out of food. They then take the carbon dioxide that's present to produce methane. Right? And we see this in marine sediments as well. So again, it's a balancing act. And as you go down with higher flow rates, when the nitrate removal gets worse, the greenhouse gas production gets better. And so essentially what we need to do is not create these systems willy-nilly. Because sure, we can over-design these systems. We can make a 10-foot wide barrier, right? And then we get nitrate removal maybe in the first foot or so, but then we'll be producing methane for the next 9 feet. So this isn't an art, it needs to be a science in order to hit these two balances, because we don't want to do pollution swapping. Term actually got from Molly and her PhD. We don't want to be trading one pollutant for another. Niels has also looked into at a given how much nitrogen can remove per foot of a permeable reactive barrier at different temperatures. Of course, we need to consider the temperature of groundwater changes annually. So, but by having this data for different wood types, we can then design these systems optimally to be the right thickness to ensure we're removing an optimal amount of nitrate. And then with this data, Niels has collaborated with other scientists to actually create models to say if you created different types of PRBs maybe of different thicknesses. So here's a 2.5 foot, 5 foot, and a column array system. And here he's modeling the groundwater flow rates, but he's also modeling the amount of nitrate in the groundwater as it flows through. So you can see in all cases, as I've described to you, the water is actually drawn into the barrier, and it has higher flow rates there, and that's what's shown in the top images. But what this also shows you is that, again, you get rate removal at 5 feet thick down to 0. But we also know that's going to be producing methane. And the column array not doing as well, but probably not producing any, and maybe the best as the 2.5 foot thick barrier. But ultimately, what we want to do is test this in a real world setting. And that actually was done in collaboration with Cornell in Hampton Bays, where a 100-foot long permeable reactive barrier was installed. This was done with Town of Southampton Community Preservation Funds, and done in a very exciting scientific way. So it wasn't just a big barrier that's put in and will treat the groundwater, but it was actually done using these different types of cells. So it's 100-foot long, but within that embedded more than 12 cells of different types, 2.5 feet thick, 5 feet thick, a column, and then a control, of course, to make it a good experiment. And so you can see Niels, being the astute scientist he is, created what's known as a randomized block design. So across the 100 feet, you can see different cells being put forth, and these are fully instrumentated. So firstly, the ability to test the groundwater in the cells, but then also the ability to put instruments in so you can understand what's happening in the groundwater that's flowing through. And here's just some images of that. These bulkheads have to have holes in them so the groundwater can actually get out. Incidentally, because it's a bulkhead on a bay, it actually lets the seawater in, but thanks to Molly's research, we discovered during our dissertation that doesn't inhibit the performance of the PRB. And you can see the different the different test cells being put in. So the column array being put in, and the different thicknesses of the PRBs. And then once it was sealed up, we were all set to sample these, both by collecting the groundwater and also having instrumentation. And then I'm not going to go through all the detail here, but this is an instrument embedded within the PRB to give us minute-by-minute dynamics of things like the oxygen level, the temperature, the salinity. We actually do get a little bit of saltwater intrusion. But this is a data set from our 2.5-foot wide cell, essentially showing that it stayed anoxic the whole time, which is what we want to some extent. That's going to facilitate the denitrification. And here's just some examples of the nitrate removal for these different cell types. And so what I'm showing here is we have, of course, as a great scientist knows, we have replication for all these, so triplicate cells. So here's the column, the 2.5 foot and 5 foot, colorized. The blue is the groundwater coming in, and you can see it varies a lot, the levels of nitrogen coming into these systems. And the green is what's coming out of them, and then we have one in the inside as well. And so what you can see at the 5 foot, again, does its job, removes all the nitrate. Get also very good, but not complete removal at 2.5 feet. And the column also removing a lot of that nitrate, but not as well as the 2.5 foot cell. And so there's a lot more to do on this going forward, looking at greenhouse gas formation, for example, and also testing this over time. This is only really just months after the installation. This will continue to happen and continue to look at, again, the effects of things like tidal zones. At the center, we have then the other reactive barrier projects going on. One is a column array or a carbon array in Georgia Pond. In collaboration with Cornell, we're doing work in Acabana Harbor and also working with Cornell at Shirley Beach to see where we might be putting a PRV there. And we have an application in to look at potentially an injection well in Southampton, the Gaggle. And so, again, as you heard Charlie say many times with regards to tool in the toolbox, well, here are PRVs as another tool in the toolbox, right? We want to address on-site wastewater. We need to have sewage treatment plants. We also need to have approaches once that wastewater nitrogen gets out. And here's another tool in the toolbox. Clearly, the lesson we're learning as we do this is they need to be effectively designed and suitable for the site. You need a lot of data on what the nitrogen levels are, what the flow rates are, to make sure they're ideally designed. But when we do on a cost-benefit analysis, it looks like on a pound-for-pound basis that if you choose the right site, this can be cost-effective. And so we'll be continuing to find sites and look at their effectiveness of these systems and removal, the production of secondary byproducts, and also advancing those models. I'm just going to transition now as we get to the end of this section. Again, it's all about what can be done with the nitrogen once it's into the systems. Charlie introduced us to bioextraction, and again, the two main approaches in that front are seaweeds, as Charlie talked about, and bivalves. I'll just mention momentarily at the center, we're not really doing a lot of work with bivalves, but there's a lot of work done by SOMAS, for example. And the effort there, on the one hand, is very, very obvious. Bivalves are filter feeds. As they feed, they're pulling in plankton that are rich in nitrogen, so they're pulling it out of the system. A second thing that they do that's actually quite interesting is that they're depositing that nitrogen onto the sediment floor. So in some sense, you may believe that, okay, well, it's not just moving the location. But some recent research out of SOMAS, yet to be published, but will be forthcoming, shows that nitrogen that then for example, clams would put into the sediment does get denitrified. These organisms are moving and they're doing the same thing actually that happens in our NRVs, coupled nitrification and denitrification. As Charlie alluded to, seaweeds do a great job of removing nitrogen, removing carbon. They're also creating oxygen, something that can be in short supply in our coastal waters. And as Charlie also alluded to, at the center, we're doing a lot of work looking at seaweeds that would be seasonally appropriate. Charlie keyed in on Gracilaria and on Kelp. We've also done work on Ova, a green seaweed that actually has a longer growing season than Gracilaria does. And so we're testing all of these different seaweeds. And again, the idea is that can you put in aquaculture kelp or other seaweeds to remove the nitrogen? And indeed, we're showing that is the case. Just showing some data here from different sites. And what's really nice about kelp and other seaweeds is the higher the nitrogen is in the ambient environment, the more they actually remove. And which essentially means that if you've got a high nitrogen environment, you're going to get a lot of nitrogen out of the ecosystem, which is exactly what we want. We've also done some nitrogen isotope tracing to understand where that nitrogen is coming from. And no surprise, when we've done the work on Long Island, the kelp that we're harvesting has an isotopic signature that's almost a perfect match to wastewater. So not only is it, so we know, which is not surprising to us, that's the biggest source of nitrogen, and that's the nitrogen that they're removing. Before I turn it over to our next speaker, I'll just mention that beyond removing nitrogen, Charlie kept saying ecosystem services. There are some pretty exciting ecosystem services that are coming out of research with regards to seaweed. Now, one is very, very obvious, and that is via the process of taking out carbon dioxide. That's the exact opposite of carbon dioxide production. That's our whole climate change problem that we have. And so in the ocean, we have something known as ocean acidification. More CO2 is driving down pH, lowering the pH, lowering the amount of carbonate ion, and essentially making a chemical environment that's less hospitable for bivalves. But we found that kelp can actually reverse that whole process. And in addition, we found that they can actually fight harmful algal blooms, which was not necessarily something we thought about going in. Now, I can talk about all these things for hours, but I won't. I'll just have to refer you to these papers that we published very, very recently. You can see the two on the left, where we've shown not only do seaweeds combat ocean acidification to change the chemistry of the seawater, but that when you co-culture those seaweeds with bivalve, they benefit. And actually, they're protected against ocean acidification. The most recent paper we actually just published just last month. And then finally, you can see a series of papers that go back more than a decade, but we continue to be able to find that seaweeds are secreting secondary metabolites, we call them oleochemicals, that actually can kill off and lyse harmful algal blooms. So if you think about this, this is a perfect marriage. You put seaweeds on an oyster farm, and you're protecting those oysters from both ocean acidification and harmful algal blooms, technically probably two of the biggest environmental threats they may face. Now, to give just a little bit more nuance on seaweed work, I'm going to introduce our next speaker. But just 1 week ago today, the New York Times ran a full-length feature article on, and he was deemed by the New York Times the Johnny Appleseed of sugar kelp. And I would say that is the case certainly in New York State. Mike Doall, who is the Associate Director for Aquaculture and Shellfish Restoration at the center and at the university actually, has introduced kelp to oyster farms all across the New York State, and he could tell you what's been done recently to use some new methods for getting it into shallow water environments across New York State. So, Mike, if you would.
Okay, thank you. So Charlie and Chris have already given a great background on nutrient bioextraction, and so I'm just going to jump in to present some results from field studies we've conducted over the last 4 years to evaluate the feasibility of farming sugar kelp in shallow waters in the estuaries around Long Island. And I'll discuss the implications this has for nutrient bioextraction in the New York mariculture industry. I want to first start off by explaining why we felt it was important to get kelp into shallow waters and to boldly grow where no one has grown before. Okay, so a little background. Commercial mariculture in New York can be found in the 3 main estuarine systems surrounding the island, including the Long Island Sound to the north, Peconic Estuary on the east end between the forks of Long Island, and the Barrier Island lagoons along the South Shore, which are collectively referred to as the South Shore Estuary Reserve. So most of the commercial mariculture is concentrated in areas where there are public aquaculture leasing programs, and that's particularly in the South Shore Estuary Reserve and the Peconic Estuary. Currently, marine farming in New York is exclusively focused on one crop, oysters. The industry is primarily composed of small owner-operated farms that are 10 acres in size or less. And of the 51 active New York marine farms reporting production in 2019, all except for one cultivated only oysters. So there's a need for crop diversification in the New York mariculture industry. And over the last 5 years, there's been a growing interest among New York oyster farmers in growing sugar kelp to diversify crops, create added revenue streams, and improve water quality. While at the same time, there's been a growing interest among coastal managers in using restorative non-fed aquaculture, like kelp and shellfish farming, to extract excess nutrients from coastal waters to help mitigate the impacts of eutrophication as Chris and Charlie have already discussed. But shallow water depths are a potential limitation to kelp farming in New York waters. It's particularly true in the South Shore estuary, where depths are generally less than 10 feet. And many of the oyster farms are situated in waters that you can stand in at low tide, like the Great Gun Shellfish Farm in Richards Bay, shown in the picture here. Shallow embayments with low flushing are also often the water bodies most impacted by eutrophication and harmful algae blooms, like brown tides and rust tides shown in the pictures here. And they're the areas where nutrient bioextraction is most needed to improve water quality. Now, the reason that shallow waters may be a limitation is because kelp is typically farmed in much deeper waters, usually greater than 20 feet, with the conventional wisdom being that kelp needs to be kept off the bottom for better growth and to avoid grazing and fouling. However, there are no studies that we're aware of that demonstrate this conventional wisdom to be true. So about 5 years ago, Chris and I set out to determine if sugar kelp could be farmed in shallow waters around Long Island for the purposes of nutrient bioextraction and diversifying New York's mariculture industry. The first thing we needed to do was figure out how to adapt conventional kelp farming methods for shallow waters. So to quickly review the conventional method, kelp is grown from suspended horizontal lines that extend between two moorings, as shown in the diagram here. The lines attach to the mooring lines at a fixed distance below the surface, usually between 3 to 6 feet. And buoys are used to help suspend the line and maintain its depth below the surface. So the kelp line rises and falls with the tides. But as we found out, it's very difficult to suspend a line in the water column at water depths below 4 feet. At these shallow depths, the suspended lines often hit and scrape along the bottom at low tide. And in addition, shallow areas are often more prone to ice, which can grab surface buoys and wreak havoc on suspended kelp lines. So for areas where mean low water depths are below 4 feet, I developed a stake line system in which a 100-foot long kelp line is staked a fixed distance above the bottom using screw-down anchors at each end. I typically use 4-foot screw anchors and screw them in the ground about 3 feet, so kelp lines are staked 1 foot off the bottom. And so as opposed to suspended lines, staked lines remain in a fixed position above the bottom and do not rise and fall with the tides. So over the past 40 years, we've conducted kelp cultivation trials at 16 locations across the island, from as far west as the East River in the Bronx to as far east as Fisher's Island in eastern Long Island Sound, and across low tide water depths ranging from 40 feet to as shallow as 2 feet. The locations are color-coded on this map to show you where we use stake lines in less than 4 feet of water and where we use suspended lines in deeper waters. And overall, we've successfully grown kelp to some extent at all but one of these sites, but with large variation in kelp growth and line yields among sites. So I'm now going to move on to the results section of this talk and show you some of this variability in kelp growth that we've observed around Long Island, with particular emphasis on comparing shallow and deep water locations. We're just wrapping up our 4th season growing kelp, so I'll be focusing on data from the first 3 field seasons. And just to define a kelp growing season, if you're not familiar with kelp farming, it extends from December when the lines are seeded to about May or June when water temperature is warm and the kelp starts to degrade. Okay, missing a slide, but that's all right. First thing I want to point out is that we've had reproducible success in the shallowest of waters using stake lines. I had some photos here showing that, but take my word for it, we've grown a very large kelp. I'm going to show you the data now on this slide. Not only did we have success growing kelp in shallow waters, it's also been among the highest growth we've obtained anywhere around Long Island. So this figure compares kelp growth among sites and years in different estuaries around Long Island that vary in water depth. The sites are color-coded as shown in the map on the bottom, and the figure tracks the weight of the kelp per meter of line over the course of the growing season. As you can see, our highest yields across years and sites have occurred in the shallowest waters in the South Shore Estuary, in Mauritius Bay colored in blue, and the Great South Bay colored in green. Growth in these shallow locations kicked in much earlier in the growing season compared to deeper locations in the Long Island Sound, which are shown in orange, and also the Peconic Estuary, which is shown in red. But shallow locations did experience an earlier onset of deterioration from fouling, grazing, and senescence in late spring as water temperatures warm. Now, one thing I want to make clear is that the higher growth in these shallow estuaries is not because kelp grows better on staked lines versus suspended lines. In 2020, we set up an experiment to compare growth on staked versus suspended lines within a site. We chose the Lucky 13 Oyster Farm in Great South Bay for this experiment because water depths there range from 3 to 10 feet across the 5-acre lease, which allowed us to set up both types of lines in close proximity. We found similar growth between the two cultivation methods within this site, shown by the 2 green lines on the graph, but large differences in growth on staked lines between separate bays. And this indicates that the differences in kelp growth among sites reflect environmental differences rather than differences in the cultivation method. I also want to point out that this year, following in Charlie's footsteps, we obtained very high growth using suspended lines in deep waters in the East River. The data for this year is not worked up yet, but I can tell you it was among the highest growth we've seen anywhere in any year, and equally as high as the growth we observed in the shallow waters of Mauritius Bay. Meanwhile, kelp growth in the deep waters of the Peconic Estuary, where we used the exact same seed stock and methods as the East River, was much, much lower, as you can see in these pictures. In addition, the kelp grown in the Peconic Estuary is much paler in color, which is often associated with nutrient limitation. And overall, our preliminary data and analyses thus far suggest a variation in kelp growth among sites is largely due to the amount of nutrients available, and in particular, nitrogen. So shallow water kelp farming works, and it offers the potential for very high crop yields in shallow bays where there are oyster farms or there's a need for nutrient bioextraction. Extrapolating from the line yields we've attained across years in shallow waters, we've estimated that a 1-acre shallow water farm can produce between 32,000 to 72,000 pounds of kelp per acre. So I'm now going to just conclude with some quick nutrient bioextraction calculations for shallow water kelp farming using the data we obtained from Mauritius Bay. And to calculate the amount of nitrogen removed, we first need to convert crop yields from wet weight to dry weight, which we can do using the linear regression we found between wet and dry weight. But basically, overall, dry weight is about 10% of the wet weight. Next, we need to know what percent of the kelp tissue is composed of nitrogen, and for Mauritius Bay, we've measured between 1.83 to 1.99%, a very, very tight range between years, and that was at the time of harvest. And then multiplying the dry weight of the kelp tissue by its percent nitrogen content, we estimate that a 1-acre shallow water kelp farm can remove between 55 to 136 pounds of nitrogen in one growing season. And just to put that in perspective, this is the annual nitrogen removal equivalent of 5 to 11 innovative alternative septic systems. So that's it for me. I'm going to end there. Thank you, everybody. That's it.